And we'll start with Ryan.
Professor, could you make me presenter?
Oh, sorry. Yes, I need to make you guys presenters. Ryan. All right. Yes, you're presenter now.
So for this question, it asks us to find the Taylor approximation of a linear function. It kind of turns into a proof. I'll get into that, but it's actually kind of an interesting proof. So, so the first part asks us to find the first order Taylor approximation. So that's basically a linear approximation. It's the first, it's the approximation with one derivative in it. So in order to get that, first, because it didn't give a center point, I just put x naught comma y naught, and first you plug that into the original function, and you get typically a number out of it, but sometimes, like in this case, just a bunch of variables. And then you take the derivative with respect to x, and you also take the derivative with respect to y, and you plug that point in for both of them. However, in this case, because we have ax plus by, the partial derivative with respect to x is just a, and the partial derivative with respect to y is just b, so which are both constants. And plugging that into the function, it basically ends up being the first part, which is this, plus whatever you get out of here times x minus the x part of the center point, and then whatever you get out of the y derivative, basically the same thing. And simplifying that, you can actually see that these two will actually cancel out with this and this. And so what you get is the linear approximation for a linear function is the linear function, because there's no point in approximating it when it's already linear. When you continue that and get a second order approximation, so that's you basically get a quadratic approximation, you're going to see that you derive a constant, and so you get 0. And of course, you need to take a second x derivative, but you also need to take an xy partial derivative and a yy partial derivative, and they're all 0. At least in this case, because the original function was linear. And so you basically just add 3 zeros and you get the same thing. You get the original function back. And then it finally asks what higher order approximations look like. And of course, if all future derivatives are going to be 0, your approximation is just going to be 0. Well, is going to be the same linear function plus those 0.
Great. Yes. Yes. Thank you, Ryan. Anyone has any question? Great. Thank you, Ryan. And Jazelia 3.29.
All right, let me just share. Can you see my screen?
Yes.
So I wanted to do 3.2 question 9, which says calculate the second order Taylor approximation to f of x comma y is equal to cosine x times sine y at the point pi comma pi over 2. So I decided to just do all my calculations first, and our first calculation we would need for the formula is f of x comma y, which in this case is pi comma pi over 2, is equal to cosine x times sine y. So for f of x comma y, all we have to do is substitute in our x value and our y value. So I did cosine x, which is cosine pi, times sine y, which is sine pi over 2, is equal to -1 times 1, so we get -1. My second calculation was to find the derivative with respect to x of pi comma pi over 2. So I did cosine x times sine y, and I took the derivative of each with respect to x, which gives us negative sine x times sine y is equal to, just plugging into our x and y values again, negative sine pi times sine pi over 2, which when we calculated gives us 0 times 1, and anything times 0 is just 0. So my third step was to do the partial derivative with respect to y of pi comma pi over 2. Again, I just took the derivative with respect to y. So this time cosine x sine y becomes cosine x cosine y. Plugging in our x and y values, I get cosine pi times cosine pi over 2, which gives us -1 times 0, which gives us 0 in the end. So my fourth step was to do f of xx. So I just took the partial derivative of f of x again, basically. So when we take the partial derivative, again, we get negative cosine x times sine y. I substituted in pi for x and pi over 2 for y, which gives us negative cosine pi times sine pi over 2, which when we calculated gives us 1 times 1, which is equal to 1. And then I took the partial derivative of, again, with fxy. And so when I did this one again, I got negative sine x times cosine y. Plugged in again, I got negative sine pi times cosine pi over 2, which gives us 0 times 0, which is equal to 0. Then I did f of yx for step 6. When I took the partial derivative there, I got negative sine x times cosine y, which is equal to negative sine pi times cosine pi over 2, which just gives us 0. And then my final calculation I had to make before plugging into the formula was f of y, which gives us negative sine y times cosine x. I just put the y in the front this time so I could have that negative in the front. So I did negative sine pi over 2 times cosine pi, which gives us -1 times -1. A negative times a negative gives us +1. And then my last step was just to plug into the formula. So our second order Taylor approximation was -1 plus 1/2 times x minus pi squared plus 1/2 y minus pi over 2 squared.
Great. Very nice. Very clear. Thank you, Cecilia. Israel, 3.125.
Okay.
Then Muhammad Zeman, 2.59.
There we go. Okay, so for 3.1.25, it asks us to basically use the Laplacius equation, which is just the partial or the double partial derivative of u of doing double partial x plus the double partial of u while doing y.
We call second order.
Second order, pardon me. I forgot its name. So, yeah. So basically on the left, I have my x's, just doing them all at once, which is, so doing the first partial derivative gives me 3x squared minus 3y squared. And because y is a constant now, it just becomes 6x when we do the derivative again. Now for the right,
yeah.
It's just, on the right, we do the y partial derivative. So we immediately get a negative 6xy because x to the third is already a constant, so we get rid of it. And for the second, doing the partial again, it gives us negative 6x. Of course, adding them together will give us 0, showing it's harmonic, which the question asks us to do and to confirm.
Yeah, the question itself is simple, but the idea is deep.
Mm-hmm.
Yeah, when we talk about a function as a harmonic, talk about Laplace equation. Laplace equations is a very famous differential equation. All right.
Yep.
Thank you.
Okay, I'll stop sharing.
All right, let's see. Okay, Muhammad Zaman, right? Then Junyi.
Yes.
Then
Do you see my screen?
not yet. Yeah, coming up. Yes, now.
Okay, so I couldn't present this one. I had it done. I just wanted to show it real quick. This is 2.5, question number 9. It says find the f in respect to the t 1, 0, where f uv equals cosine of u sine of v, and it's defined by t, s, and t, which equals cosine t squared s and log of square root 1 plus s squared. So right here. So this is basically partial derivative. You do the partial derivative and you get the simplified answer, which is right here. Let me present it step by step.
Partial derivative of composition functions.
Yes.
Yeah. So which makes it a little bit complicated.
Yes. So first up is the composition. So we take the f uv function, which is cosine of u sine of v, and we take the t s comma t function cosine of t squared s and log of square root 1 plus s squared. We do the composition. These are the functions, and when we simplify them, I got cosine times t squared s times s sine log of square root 1 plus s squared. So this is the composition that's done. Then after that, I basically just did the partial derivative. So these are the steps. It clearly shows how it went through. I'm gonna go down 1 minute. So f in respect to t, s comma t. This is what it equals. If I go down, I finally get right here cosine of cosine times 0 times cosine of
Not times 0. It's cosine of cosine 0.
cosine 0, yes, and then log of
Cosine
square,
of log square root of 2.
cosine of log square root of 2, yes, and then 1 square root of over square root of 2 again times by itself plus 0. And when we simplify that, so we're trying to find it for the point 1 comma 0. So when we plug in the points, there we see the 1s and the 0. The simplified answer is half cosine of 1 times cosine of log square root of 2, and this answer is confirmed by the workbook. 2.5, question number 9. That's it.
Okay. For the purpose of review, I'm going to ask you a couple questions. Okay, can you bring them back?
Yes.
This question is good for review. Can you go to the top?
Go
Because
to
that's
the,
another way. That's another way of calculating the derivative of composition of two functions. Can you remind us what is the way to calculate that? So this is one way. There's a second way to calculate it.
so you mean the, I'm sorry, what's the question?
Something's called chain rule. Okay. Calculating the derivative of composition functions, we have two ways of calculating it. So you showed one way. There's another way. Another way, remember, by chain rule. Let's see your function, right?
Okay.
Let's see your function.
Let me pull
Your
up the,
function.
yes, there we go.
Right. So function f, can you tell us what kind of function is f? So this is a review for everybody. Okay, when I ask Muhammad questions, I'm asking all of you, okay? Okay, Gregory is answering
yeah.
for you.
The chain rule.
Chain rule, right, is another way. So if we use the method of chain rule, what do we do?
So we do the derivative of the first one times the second one.
Exactly. So we're going to have a multiplication of two matrices.
Yes.
There's a capital letter DF. So can you tell me what's the dimension of DF? Well, think about the F. F
Yeah.
is a vector function. F goes from what space to what space?
So
Look at the function F.
okay.
Maybe go back to the question itself.
Okay, the workbook. There we go.
Yeah. Okay. So look at F. Staring at F. What kind of function is F? So F takes what kind of vector?
2D.
What dimension? The domain, yes, two
Okay.
dimension, right?
Dimension? Yeah.
Let's go back to the question, right? So F goes from two space
Oh, it shows
to
it right
one
here.
space. So F goes from two space to one space. So what is the capital letter DF? What's the derivative of F? I only need to know the dimension. So I always emphasize on dimension count. All right, you have to have the dimension count first.
Oh, okay.
So what's DF? What's the dimension of DF?
The derivative of f.
Yeah, capital letter
So it goes
DF.
from 2 to 1, right? So it's gonna be 1 because it goes from 2 to 1.
Dimension of a matrix. So matrix has a number of rows, number of columns. How many columns it has? How many dimensions? Muhammad, would you please bring the question back?
Oh yeah, sorry. Okay, there we go. You see it?
Not yet. Okay, yes. Right, because you are presenting this question, right? So I need to ask, because this is important for all of us to review. So that's why I'm asking you some questions, and this question is for everybody to think and answer. Something's going wrong with your screen.
You don't see it? It's open.
It's something
How
is,
about now?
it's okay. I can share my screen. Oh, it's back.
It's back. You see it now?
Yeah.
Okay, there we go.
Okay. So DF, can you tell me the size? Because we know capital letter DF, the derivative of F is in the matrix. Can you tell me the size of this matrix?
So you said it's 2 to 1, right? The dimension.
The dimension 2 to 1, or is 1 to 2? 1 by 2. We call 1 by 2.
So yeah, 1 by 2.
It's 1 by 2. Can you tell me why it's 1 by 2?
Let me see 1 minute.
Because the codomain, look at F, staring at F.
Yeah.
F takes two space vector to one space, right? It's a real value function. So it's one space. So the size of codomain is 1. The size of domain is 2. So DF is 1 by 2 matrix. Or we call row vector. Does that make sense?
Yeah. So the size of the matrix, it's dependent on the number of rows and columns.
The size of DF depends on its dimension of domain and the codomain. When I
Okay.
see domain and codomain, does it make sense to you?
Yeah.
Okay, what's the size of domain of F?
So is Are you talking about the dimension itself?
Yeah, right now I'm asking the dimension of itself. F goes from what dimension space to what dimension space?
So 2 to 1.
2 to 1. All right. So T goes from which space to which space?
So is it the opposite?
What do you mean the opposite? Look at it. Look, stare at the T. T is right in front of you. Function T. What's
So
R2 to 2?
so it goes from 2 to 2, yeah, right here.
Goes from 2 space to 2 space, right? So what's dt?
So 2 to 1.
2 to 1? Why is it 2 to 1?
So t goes from 2 to 2. You said the derivative of t, you want to know the
Yeah,
dimensions of that?
that's right.
So let me see, 1 minute. Does it stay the same?
Oh, no. No, you have to study harder. So who did the homework for you?
No, Professor, so this is just one of the questions. So it stays, yeah, so it stays from 2 to 2, right? The d of t as well.
dt is 2 to 2, 2 by 2 matrix. Why? Can you tell me why dt is a 2 by 2 matrix?
Because 1 minute.
I'm asking basic questions. If you do not have this framework in your head, how are you going to do your homework?
Is it because of the rows and the columns? It's because of the columns and the rows, right? The dimensions.
Okay, when we talk about,
Yeah.
I'm scared right now. I hope only he has a question, nobody else. So let's look at this F. F goes from n space to m space. What is the dimension of df? Mr. Zaman, please answer this question. What's the dimension of df? What is df, by the way?
The derivative.
The derivative, what is it?
So it's 2 to 2.
No, right now it goes from n space to m space, almost 2 to 2. Okay, stop typing. Everybody, stop typing. And I want to know how well is Mr. Zeman doing in this class. All right, stop typing anything. So F goes from n space to m space. What is df? How does df look like?
So
You have no idea. You can tell me you have no idea.
is it r to the m to r to the n? So the
Okay,
opposite?
Okay, let me ask you this. What does r to the n mean? What does the space n space mean? N space mean? What does this sign mean? Rn. What does this mean? What does this mean to you? What does space m mean to you? What does
So,
Rm
so
mean to
the
you?
so is Rn the domain? right?
Rn is called domain, but what does it mean to you? When you look at Rn, what's in your head? When you see n equals 2, what's in your head? When you see n equals 3, what's in your head? What kind of picture you can picture in?
So it gives you the picture of the columns and the rows of the matrix, right? So this is the domain of.
When you see Rn, you see the matrix?
No. So this is the domain, right?
This is domain. What does it mean? What does it mean? Yes, it's domain, you're right. Yeah, when we see f goes from R2, let's see, to R3, what kind of picture in your head? What is R2? What is R3?
The points and the vectors.
So R2 is 2 space, right?
Okay. Yeah.
You have 2 axes. So R3, what you have?
3 spaces.
R3, 3 spaces. So what do you have?
A
How
2 by
many axes?
3. How
You
many
have
what?
3
I'm sorry.
You have 3 axes.
Yeah.
So n space means
The
so
number
this
of spaces.
n space means you have n axis. So 2 space means you have x-axis, you have y-axis, orthogonal to each other. N space means you have n directions, you have n axis orthogonal to each other. This is called Euclidean space. Does it make sense to you? Can you make a picture
Yeah.
in your head? Okay,
Yeah.
so M
Now.
space, so now can you tell me what's the M space? What's the M space? How many axes you have?
3.
I'm talking M. You have M
Oh.
axis, right? Right. So then what is DF? DF is M by N matrix.
Okay.
So why? Because in the codomain, you have M components. You have M directions. You have M axis, whatever you call it. You may have F1, F2, up to Fm. Remember that?
Yeah.
Okay, now your domain has n axes, n components, or n variables. You may call x1, x2, up to xn. So you have to take a partial derivative of each component in the codomain in respect with each variable in the domain. So what do you have? You have m by n matrix. You have m rows, n columns. You have partial f1 with respect to partial x1, the first row, up to partial f1, partial xn. Does that make sense?
Yeah. So that's the derivative. Okay.
No, that's the derivative for the first component in the codomain. You do partial f2, partial f3, so on. The last row is partial fm with each variable in the domain. If you still have problem with this, how are you going to take the first exam? How are you going to take the midterm?
I got it now.
All right, so please All right, anyone has any questions? Okay, from time to time, when it comes to important concept, I will initiate the questions like this, all right? June E, 3.11.
Okay, please give me 1 second, because I don't have my mouse here. I have to click it. Okay, please give me 1 second, because I don't have my mouse here. I have to click it, and it's
Well,
to do.
like if you know you're almost to present, try to get ready for it. Okay, next one will be Yuri, then Gabrielle, then Josephine, Adam, Dayeli.
Okay, whoosh. Okay, so for this question, I'm presenting the question, chapter 3.1, number 1. It's the division, and we take the derivative of it. So this basically the main thing is followed by the quotient rule. So we take like the top over the bottom. We take the bottom times the derivative of the top minus the top times the derivative of the bottom over the square root, the square of the bottom. So I got the partial square f and the partial s over the partial x equals to 2y times the y square minus 3x squared over the x squared plus y squared to the third.
Your work is gone.
Can anyone see it?
Yeah.
No. Okay. So so the partial square of f over partial of y. So we take the same followed by the quotient rule. I got the answer of 2x times the x squared minus 3y squared over the x squared plus y squared to the square to the third degree. And we take another derivative of the partial x. And then I got the 24xy times x plus y times x minus y over the x squared plus y squared to the fourth degree. And the partial y squared, I got basically the same thing, but they switched the y and x position. So there's 24xy, y times y plus x, y times y minus x over x squared plus y squared to the fourth degree. And then the partial x and times the partial y. I got the negative 6 times the x squared, not x squared, 6 times the x to the fourth and plus y to the fourth minus 6x squared y squared over x squared plus y squared to the fourth degree. And the partial y times partial s, the same thing, but just switch. Well, not the switch, just basically the same answers as the partial x and partial y. So which is
So what can you conclude? Okay, go ahead, finish.
Yeah, so basically it's the same. So it's negative 6 times the x to the fourth plus y to the fourth minus 6x squared y squared over x squared plus y squared to the fourth degree.
Okay, again, a presentation is not about reading off what you write. All right, it's about explaining the concept behind. Okay, so what can you conclude from your calculation?
Well, basically, from what I saw, so I see the partial derivative of x and y. They just switch the x and y from, well, the same thing, but just like the first one derivative, like 2y, when do the partial x, and since I do the partial y, it goes to x for that.
You could write for this part, for the y part, you don't really have to show the calculation.
Oh.
For those two. Why? Because you observe the function. If you switch the position of x and y, does the function change? You switch the position of x and y. You read x as y, you read y as x. does the function change at all?
I don't think so.
No, right? So this
No.
means this function is called symmetric. So x
Oh.
and y equally weighted. In this case, if the function is symmetric, it means the two variables, are equally represented. Once you calculate the x, you can see because the function is symmetric, you get this answer right away. You just switch the position of x and y.
Oh,
Okay,
so
what can
like
you
basically we do the partial x. When we do the partial, we get the answer of partial x. So we do the partial y. We just switch x and y. That would be it. We don't need to calculate it all.
You don't need to calculate because when you see these functions called symmetric functions, x and y are equally represented.
Okay.
So what can you conclude with a mix of second derivatives? They called mixed partials.
Well, yeah, even though like they switch the order of like partial x, partial y, or partial y, partial x, they got the same answer.
Exactly. So in Euclidean geometry, mixed partials are equal. A very important concept. All right, that's for GE. Thank you. Yuri, 3.319.
Yes, it's over here. So my question that I want to present reads: find and classify all critical points of the function given. I'm not going to read the function; it's pretty long. So basically, there is a clear procedure for finding critical points of the function and classifying them. And I want to show how we do this. So the first step is to find.
Yuri, just hold on 1 second. So Yuri is going before us, I think. You are, because I haven't talked about critical points yet. I haven't talked about minimum, maximum, but go ahead, just go slow, explain to us the concept behind. It's very similar to single variable calculus. Just do partial derivatives. All right.
Yeah.
So thank you.
Actually,
go ahead.
There is not much new information. Actually, all the thing is familiar to us from previous chapters. The method of finding is kind of new. So the first thing what we do, we just we find the partial derivatives with respect to x and with respect to y, and then set them to 0, both to 0. And we solve the system of equations with fx is equal to 0. Fx by fx, I mean partial derivative of f with respect to x, and by fy, I mean partial derivative of f with respect to y. So we have the system of two equations, fx is equal to 0 and fy is equal to 0. I'm sorry, I have a kind of mistake over here. It should be just x, not x squared. When I find the partial derivatives, I got two functions over here, and when I solve the system of equations, I can get the result. The x's and y's which solve these equations are x is equal to 0 or x is equal to 1, and for y it's y is equal to 2 and y is equal to 3 over here. So, and these solutions give us critical points, actually. So we kind of combine them, these solutions, x's and y's, to get the following critical points over here. So for these points, go from this part, like 0, x is equal to 0, x is equal to 1, over here, they're all there. So kind of combination of x's and y's. So in this particular case, I found 4 critical points, and then I have to classify them. For this, I go to step 2, which includes finding the second partial derivatives with respect to y and with respect to x, and mixed partial derivatives as well. So just for the notation, fxx is the second partial derivative of function f with respect, not function f, sorry, of partial derivative of fx, but actually, like, this is the derivative of derivative, so it's kind of second derivative, derivative of this function. Fyy is derivative of fy, fxy is derivative of fy with respect to x, and fxy is derivative of oh, I'm sorry, it's like, oh no, it's not a mistake. Actually, it's like, as it was told before, fxy is equal to fyx because of the symmetry, so we don't need to find two of them. So they're
because mixed partials, are equal in Euclidean geometry.
Yes, exactly. So I have only one here. So when I find these derivatives, actually the function is not very complicated, so the derivatives are pretty simple, and I'm not going to read them. And then we find that the third and last point is that we have to find the discriminant of the Hessian. By the Hessian, I'm sorry, I don't have it here, so it should be like the matrix. In our case, it's 2 by 2 matrix, and here, sorry, I don't have a mouse, so my handwriting is going to be pretty bad, but it's something like this, like fxx, and then fxy, and here will be fyx. I'm sorry, I'm not going to write it anymore. Fyx and fyy. So, and to find the determinant of the Hessian, we kind of cross multiply them and subtract fxx. So the formula is over here, fxx times fyy minus fxy times fyx. But because fyx and fxy are equal, I just take one and square it. And here we subtract these terms. And of course, we evaluate the discriminant at the critical points. So to classify critical points, we should evaluate the discriminant of the Hessian for each critical point. And over here, there is a quick review of how to determine if the critical point is local minimum, local maximum, or a saddle. So if the discriminant of the Hessian is less than 0, then we have a saddle point. If it's more than 0, then there are two options. We can have a local maximum or a local minimum. How do we find it out if it's a local minimum or maximum? We just look at fxx. So if the second partial derivative of fx is less than 0, then it's maximum. If it's more than 0, then it's minimum. So then I substitute. Oh, by the way, over here in this formula, this is equal to 0. That's why the formula becomes a little bit simpler, because my fxy is equal to 0 over here. So basically, what I just need to do is to multiply two functions, substituting the critical points for x and y. So at the point 0, 2, we have that discriminant is more than 0. Then there are two options. It can be a maximum or a minimum, local maximum or minimum. So I need to look at fxx at this point. In this case, it's it's -1, which is less than 0. That's why I conclude that this is local maximum. For the second point, 0,3, the result, the discriminant is -1, which is less than 0. So it's a saddle. I don't need to check fxx. For the third point, 1,2, the discriminant of the Hessian is -1, which is also less than 0. I got another saddle. And for the last point, 1,3, the discriminant of the Hessian is 1, which is more than 0. That's why I have to check fxx. Over here, I plug in the coordinates of the point and get 1 as the result, which is more than 0. That's why I conclude that I have a local minimum at this point. And that's it.
All right. All right. Thank you, Yuri. Yuri just proved a teacher is not necessarily needed nowadays. Yeah, you can self-study. Anyway, I'm going to talk about this finding critical points: local maximum, local minimum, absolute maximum, absolute minimum, stuff like that. Thank you, Yuri. Gabrielle, 3.119. Then Josephine, 3.13. Then Dayeli, 3.19. Dayeli, 3.19.
Can you see my screen?
Yes.
Okay. So number 19 of section 3.1 is basically an example of theorem 1 in the section of where we like prove the equality of mixed partials, kind of similar to Junyi's problem that you did. So basically we're given this function e raised to the power of x, y, z times sine xw, and we have to prove that the derivative of xzw is equal to the derivative of zwx. So basically what I did was solve for one side first. So first you take the original function and then you find the derivative of x, and then once you get that answer, you find the derivative of that, the z derivative of that, and then once you get the answer of that, then you find the w partial derivative of that answer. And basically this question, or like this entire chapter, isn't really like difficult per se. It's more so just like fine tuning and like paying attention to detail, because it's just like a lot of repeated product rule and chain rule. So like as you can see, there are like some parts where it's like colored so that I don't get confused. So yeah, so I solved for one part and then I got this really long answer and I kind of got confused with all the exponents and all that. So I left that there. Then I jumped over and I solved the derivative of zwx. So again, you start with z. You find the partial derivative of z for the original function that was given in the beginning. Then once you get that answer, you find the partial derivative of w of that answer. And then finally, you find the partial derivative of x for that answer. So it does look kind of confusing because it's like the partial derivative of like zwx, but you basically just take it like step by step. It's sort of like chain rule, like in a bigger form. So then I got that answer, and then thankfully it was the same answer as the first derivative. So then I basically just verified that it was correct. And basically going back to theorem 1, it's basically saying that this function is of class c to the 3, or that it's like thrice differentiable. So yeah.
Okay. Yes, the calculation is tedious. Yes, but it's not difficult. But it needs like fully to have a full attention. All right. Thank you, Gabrielle. Next one, Josephine, 3.13.
Okay, so this has you compute the second partial derivative. So it's f of xy is equal to cosine xy squared. So first I took partial f partial x, and so the derivative of cosine is negative sign, so then you leave the inside, which is xy squared, and then here you're leaving y constant, so then the derivative of x is just 1, so you get y squared, so that is negative y squared sine xy squared. And then I took the second partial derivative, so I got, doing the same thing, keeping y constant and only differentiating x, I got negative y to the fourth cosine xy squared. Then I took partial f partial y, and the same process, but instead when you're taking the derivative of the inside, since now we're taking the derivative of y, it's going to be 2yx, keeping x constant, and you get negative 2yx times sine xy squared. And now the difference with taking the second partial derivative of y is that it requires the product rule, where the second partial x didn't. So then taking the derivative of the first part, you get negative 2x, leave the second, plus now flipping, so then you get negative 2yx times derivative of sine's cosine, leave the inside xy squared, and then times the derivative of the inside of that, so that's 2yx, and then putting that all together, you get negative 2x sine xy squared minus 4y squared x squared cosine xy squared. And then taking, I think I did taking partial y, then partial x, I got, I have to scroll down because I did it in two separate things. This is also the product rule. So taking the derivative with respect to x here, you get negative 2y sine xy squared plus, now doing the opposite, negative 2yx times cosine xy squared times y squared, and putting that all together, you get negative 2y sine xy squared minus 2y cubed x cosine xy squared. And then finally, the last step is doing partial f partial x and then doing partial y, and it's the same thing when you end up getting the same answer, so the mixed partials are equal in question 3.
All right. Okay, thank you, Josephine. Okay, last one, Dayeli, 3.19.
All right, I'm gonna share my screen really quick. All right, can you guys see my screen?
Coming up.
All right, so for question 9, 3.1 is asking us to pretty much prove if there is existence of a c-square function of f times x comma y with partial of x equal to 2x minus 5y, and the partial of y equals 4x plus y. So I started by finding the antiderivative with respect to x for the first function. So I ended up with x squared minus 5x times y plus c. In this case, since I'm taking the antiderivative with respect to x, you want our arbitrary constant c to be with respect to the opposite variable. And I did the same thing. I took the antiderivative with respect to y for the second function, and I ended up with 4x times y plus y squared over 2 plus k with respect to x. And then I said that in this case, our arbitrary constant could be for c c respect to y could be y squared over 2, and then that x of x could be x squared. But now if we notice that for our first function, when we took the antiderivative with respect to x, we get -5 times x times y, and then for the second function, we get 4x times y, and I ended up concluding that they're not equal, so that this can't work, because in this case, f times y, f times x times y does not equals fy times x.
No, we don't read this way. We read a partial, this mixed partials.
Yes, the partial of x times y does not equal the partial of y times
No times in between. There are no times in between. So see, this is second partial. So partial square f, partial x, partial y, partial square f, partial y, partial x. Yeah, so this is a great example of, it's counterexample to see the mixed partials not equal. If the mixed partials not equal, this function does not exist in Euclidean geometry, but in other geometry. If you're a math major, you will learn this. Anyone has any question? All right, great. Thank you, Dayeli.
Thank you. Also, Professor, before you start class, can you like quickly go over the second order of Taylor formula? Because I'm having a really hard time understanding that part of the
Oh, okay, no problem. Yeah, it's actually simple concept. It's just it's just more involved. So 3.2. So right here, let me see if I can make this even bigger. Why not? Sometimes it's missing the, let me see this. No. Sorry, I can only maximize in the very beginning. Now I lost the opportunity to make it bigger. Okay, remember in single variable calculus, right? So the linear is this part. The linear is saying we evaluate the function at the next point. Think about square root of 4, which is a 2, is the next point. And we can use that to approximate the square root of 3.9, right? Or square root of 4.1. And make this like a concrete example in your head. So x naught representing a next point. We know exactly what it is. And the plus h could be positive, h could be negative. Just means the neighborhood points. That means the points x naught plus h is a point close to the very next point. So what do? We evaluate the function at the next point. Then we evaluate the rate of change of the function at the next point. Then multiply by the difference of the point with the next point. Right, so this is the linear approximation. If you want to do second quadratic approximation, so we would involve second derivative, right? We calculate a second derivative, we evaluate at the next point, then divided by 2 factorial. Well, 2 factorial just 2. Here we divided by 1 factorial. 1 factorial just 1, right? Then multiply by the difference squared. Right, difference squared, so on and so forth. If we want to do k level of Taylor's theorem approximation, we would go to k level of derivative. But then the function needs to be k c to the kth power, means the function can be differentiate k times. So C2, C1, C3 means that. C2 means the function can be at least differentiate twice. C3 means the function can be differentiated on at least to a third level, so on and so forth. So similarly with this, with ours we just have to deal with the partial derivatives, right? Now our x naught is not one value, it's a vector. It has a couple of components, right? So we have this matrix, derivative is a matrix, but we can write it out. We can write it out. This is summation sign. Maybe, let me see if I can find from level 2 to level 1. Then, okay, let me go to the whiteboard. That's not considering nth level yet. Let's just consider simple example. Let's see f takes two variable, okay? X goes from 2 space to 2 space. Let's do that. Just want to make up some 2 space to 1 space. 2 space to 1 space. Okay, let's see. This is let's see. This is 6x squared y. I'm just making up. Okay, some functions plus x y cube. Okay, so f just goes from 2 space to 1 space. Because Taylor's theorem is approximating a real value function. So the codomain is always 1 space. So what do we need to calculate? So let me just write the Taylor's theorem first, second order. Okay, so f of x, y, you could use h or you don't need to use h. Okay, so given a next point, x naught, y naught. What is h in the book notation? In the book notation, h is a vector. H has 2 components. H equals to, in this case, we could think, but we don't really need that. Okay, equal to what? X minus x naught, y minus y naught. All right. So we don't. I don't need to use h. All right. So what I'm going to write is this. Equals to f of x naught, next point, y naught, which is very close, which xy is very close to this point, evaluation, then plus partial f partial f in x direction, evaluate at x naught, y naught, then multiply by the difference x minus x naught in x direction, then plus partial derivative in y direction, evaluate at x naught, y naught, then multiply by the difference in y direction, which is y minus y naught. You could use h2 to represent. So this is the first level derivative. Then plus the second level derivative. Second level derivative will have f x x, right? Evaluate at x naught, y naught. Then multiply by the difference. Well, here we have divided by 2, right? Because we divided by 2 factorial. Well, let me use a half to represent half of this. The difference in x minus x naught. the second power, because this is second order. Then plus half f second order in y direction, evaluate at x naught, y naught. Then multiply by the difference in y direction square, y minus y naught square. So logic is exactly same as before. Then plus what? Mixed partials. Well, fxy, partial f, partial x, partial y, partial square f, partial y, partial x are the same. So we don't need to divide by 2 anymore because we have 2 of a half. So we just do partial square f x y, then evaluate at x naught, y naught, then multiply by the difference in x direction because it's mixed partials. Multiply by the difference in y direction. Right? Let me see. This is not such good looking. Let me move down. Okay, let me see if this is clear.
It makes sense now. I get it now. Thank you.
You get it now? Okay. All right, that's it.
Yeah.
So the concept, the logic is still the same. Okay, anyone else has any questions from previous chapters? Previous material. All right, let's go to our textbook. So we have covered 3.3, 3.1, 3.2, 3.3, and we have agreed our first exam on August 3rd, right? Okay, extremes, critical points, which Yuri already explained to us a little bit. Okay, I want to get rid of this. All right, nice. Okay, extrema of real value functions. Real value function means the codomain is one space. It's just a real number when we evaluate at a point. Maxima and minima of functions for n variables. Let's see the definition first. Yeah, homework 3, I'm gonna postpone so you can study. August 3, I'll postpone to August 7. All right. Homework 3. Let's see the definition. Homework 2, I think I changed all of them, but anyway, so I'm going to change it to August 7, so you could study, all right, which makes sense because your homework is your review. Okay, F goes from n space to 1 space. It's called having a local minimum if there is a neighborhood, okay, V. Remember talking about the open sets, okay, neighborhood of V of x naught. V means a set of points. So which means, you know, think about x naught as a center of a neighborhood. So all the points are very close to it. Think about x naught as a square root of 4, which is a 2, right? Think about square root of 3.9, square root of 4.01. All those points are very close to square root of 4, but it's not. So for all points of x in the neighborhood, if its evaluation is at least the same as the next point, so it's called a local minimum. Okay, because all other points at least, you know, this much or greater, so this point becomes a local minimum. Similarly, if this point is greater than all others, right, then it's called a local maximum. We also call relative minimum or relative maximum. And when we talk about both together, minimum or maximum, we use extrema, one word for it. So the point x naught is called critical point, same as before. All right. And how do we find it? We set derivative of f evaluation at x naught equal to 0. Well, what is the df? Gradient of f, right? Gradient of f, which is 1 by n. In this case, is a 1 by n matrix, or a row vector has n components. When does A equal to 0? When every component equals to 0. So it's a 0 vector. So it's the same as before. Before we would have set f prime or df dx equals 0. So now when we find the critical points, we set this df vector, gradient vector, to be 0, which means each component is 0. All right. How many components we have? We have n components equals to 0. So a critical point is not a local extrema. It's called a saddle point. What does this mean? Because we have n directions to consider. Maybe it's a local minimum in one direction, but it's a maximum in another direction. In different components, it acts differently. So we call saddle point. Look at this picture, local minimum, right? It's obvious. All other points in the neighborhood has greater function value than this one. And similarly, this is local maximum, right? You see the neighborhood points, evaluation of the function value is smaller than this one, so it becomes the local maximum. First derivative test, which Yuri showed us a little earlier. So this is just for mathematically setting up. All right, it's differentiable, means we know cusp. So x naught is a local extrema, means either local maximum or local minimum. Then its derivative is 0. All right. So this is if and if. So it works both ways. All right. So then we call x naught a critical point of f. Let's see an example. We want to find local minimum, local maximum of this function defined by x squared plus y squared. All right. So what do? We just find gradient f. What's gradient f? 1 by 2 matrix, or a row vector with 2 components, right? Partial x, partial f, partial x, partial f, partial y. Partial f, partial x, 2x, partial f, partial y equals 2y. Then we set those two to be 0. 2x is 0, then means x to be 0. 2y is 0 means y is 0. So the critical point is the origin, 0, 0. And the value of the function is 0. right? 0 squared plus 0 squared is 0. So 0 and 0 is the only critical point. And how do we know it's this point is a relative minimum? Because this function tells us, because it's x squared plus y squared, the least value is 0, 0, comma 0. The least value of this function is 0. So that's contributed by 0, comma 0. So that's why we know it's actually it's absolute minimum. Let's see example 2. Well, this one is defined as x squared minus y squared. Right? If we find a partial f, partial x, we get 2x. Or partial f, partial y, we get negative 2y. Right? We set x, 2x to be 0, negative 2y to be 0. We also get a 0, comma 0 to be the critical point. But what happens? If we hold x to be 0, right? Set y, so you will compare any, so if we let y to be 0, hold x can be any value. We plug into the function. We see all the points are greater than 0. F of 0, comma 0 is 0. And if we hold y, we let x to be 0, we hold y, so y runs the whole real number. Because this is a negative y squared, right? So we see f of 0, comma y is less than or equal to 0. So what does this mean? This means in one direction, 0, comma 0 acts as a local minimum. In another direction, f of 0, comma 0 acts as a local minimum. So in one direction is a local minimum. Look at this picture, right? In y direction, in x direction, in y direction, it acts like a local maximum. In x direction, acts like a local minimum. So we call this a saddle point. It looks like a saddle on a horse. So that's how it gets its name. If anyone has any question, feel free to stop me at any time. Let's see example 3. Well, this function is defined as x squared y plus y squared x. And then we also see this function is symmetric. If we change x to be y, y to be x, the function stays the same. So in this kind of function, you know, x and y are equally represented. We calculate partial in x direction, we get a 2xy plus y squared. In y direction, we don't really have to calculate. We just switch the position of x and y. We get this. Well, we set this one to be, we set both to be 0. So we get a system of equation of two equations. Okay. So this equals 0, this equals 0. So that means we can equal those two. Equal those two, 2xy offset. So that means y squared equals to x squared. That means y equals to plus minus x. Right. So I have two line worth of critical points. Well, substituting x equals y in the first two equations, what do we get? We get 3y squared, well, equal to 0. That means y equals 0. Same thing for x, right? Then, if we substitute x equals negative y, plug it into, we also get y equals 0. So that means the only critical point is the origin. Is the origin. If x equals y, the function equals to 2x cubed, right? Which is both positive and negative for x near 0. So hence, the origin is not a relative extrema. Right? Example 4 is a little bit complicated. So this is a computer drawn graph for this function. Right? This is also symmetric functions. So where are the critical points? We see this is circle worth. We see a circle worth of local maximum, right? If we do that, we do partial z, partial x, we get this. Then because it's symmetric, we change the position of x and y. We get a partial in y direction, we get this. So when x equals y equals 0, what do we get? Because this is a y equals 0, that's 0. X equals 0, that's 0. So when x squared plus y squared equals 1, the unit circle. So this is consistent with the figure, right? With the picture. Points on the creator's rim are maximum, and the origin is a minimum. The origin, we won't be able to see it. Right? It's under in the center of this under. And we see the local maximum is this circle worth, which is a unit circle. So sometimes critical points is not only a couple points. There can be infinite many points. It could be line worth. It could be circle worth. Okay, that's first derivative test. Basically, we set the gradient to be 0. The gradient of the function to be 0. Gradient of the function to be 0 means the gradient vector is 0, which means every component in the gradient vector is 0. Second derivative test. Okay, we call this Hessian of f at a next point. What it is, we use this h f of x. Remember, h is the difference in x direction or in the direction, it mentioned. So equals the half second derivative. Remember, second derivative we divided by 2 factorial, so that's why we get this half. So all the second derivatives, all right, all the second part of the derivatives, we have linear approximation, quadratic approximation. So Hessian is the sum of all the second derivative approximation. If we want to use matrix to represent, it can be represented this way. If we use summation sign to represent, it represented this way. So top has a little bit explanation, all right, if you get confused. So we call this quadratic part of the Taylor's theorem Hessian. By equality of mixed partials, the second derivative matrix is symmetric. So the Taylor's formula may be written this way, right? The Hessian. So this is the second order of Taylor's theorem. And because the second derivative part can be written as a Hessian, so this is simplified. This just means the tail, And this can be ignored. When we do approximation, this can be ignored. Okay, second derivative test for local extrema. F is real value function, and it's at least 3 level differentiable. And x0 is a critical point of f, and the Hessian is positive definite. All right, positive definite. For us, it just means positive. Okay, the Hessian is positive. And then x naught is a relative minimum of f. If the Hessian is negative, then x naught is relative maximum. This is the lemma. Okay, let's see an example. So let's go back to this function x squared plus y squared. And we know the origin is a critical point. And also we know 0, 0 is a local minimum, right? By analysis of this function, because the value of this function can be at least 0. Then we use that to, so f is already in the form of Taylor's theorem, right? F of 0, 0, and the difference in x direction square, the difference in y direction square, then plus 0. So the Hessian evaluated at the origin, just a difference in x direction square, difference in y direction square. Which is clearly positive. So that means 0, 0 is a relative minimum. In two-dimensional Hessian, we can write this way. All right, in matrix multiplication notation. In general, so second derivative test. F of x, y, class of C2 on the open set of U in R2. The next point is called the local minimum of F, provided the following condition holds. Partial f, partial x evaluated at this next point, partial f, partial y evaluated at this point equals 0. What does this mean? It means gradient f is 0. Gradient f is 0, right? Because only gradient f is 0, we can find critical point. So we set gradient f to be 0 to find the critical point. So x naught, y naught is a critical point. The second partial in x direction evaluated at this point, critical point is positive. Second derivative in x direction evaluated at a critical point is positive. Okay, with these two holds, then third one, we call this D discriminant. This D is a determinant of a 2x2 matrix. This 2x2 matrix is partial f, partial square f, partial x square, partial square f, partial x, partial y. First row. Second row, partial square f, partial y, partial x, because those two are the same. Then partial square f, partial y square. So the determinant of this 2x2 matrix, we multiply, we find a discriminant, no, we find determinant of the matrix, so we get a partial square f, partial x square, multiplied by partial square f, partial y square, minus the mixed partial square. If this discriminant is positive at this critical point, okay, has to be positive. So D is called the discriminant of the Hessian. So this is called a local minimum, all right? Local minimum, first we have a gradient to be 0, which means that every component of the gradient vector is 0. Second partial in x direction at the critical point is positive. The discriminant at the critical point is also positive. So the point can be classified as a local minimum. If the discriminant is negative, no, if partial square f partial x square at the critical point negative, and D is still positive, then we call the point local maximum. So the second one is negative, but the third one is still discriminant, still positive, and we call it the critical point local maximum. If the discriminant is less than 0, right? If the discriminant is less than 0, which means partial square f partial x square equals 0, or this equals 0, but the mixed partials not equal to 0. Right? 0 minus a non-negative value must be negative. If the discriminant is negative, then the point is a saddle point. All right. If the discriminant equals to 0, no conclusion. We have no idea about the critical point. We cannot classify it. We can only classify when the discriminant is positive and when the discriminant is negative. All right. So this works with first derivative test, right, to classify critical points. Let's see an example. We want to classify x squared minus 2xy plus 2y squared. Okay. So we find a partial f partial x, or partial f partial x is 2x minus 2y. It's set to be 0, that means 2x equals to y. That means x equals y. Then partial y, partial x, partial f, partial y, we get a 2x plus 4y. Well, 4y minus 2x. We set that one to be 0. So that means 4y equals to 2x. That means 2y equals to x. Well, x equals to y, 2y equals to x. That means xy can only be 0. So 0, 0, the origin is the only critical point. Excuse me. Then we use the second derivative test. Right? We can calculate partial f partial x squared equals to 2, partial square f partial y squared equals to 4. The mixed partial equals to negative 2. Well, negative 2 squared is 4. 2 times 4 is 8. 8 minus 4 is 4, positive. Second partial in x direction is positive. Discriminant D is positive. So the origin is local minimum. All right. In example 6, remember x squared minus y squared, and we can calculate D, and D will be negative because that one is a saddle point. That means the discriminant is negative. Excuse me. Okay, this example, yeah, go through yourself. Okay, only the calculation is a little bit tedious, but the concept is the same. In the end, we also get the origin as the critical point. Then we calculate it. We use second derivative test. We use the first derivative test to find the critical point is 0, 0. We use second derivative test to find it's a local minimum. Okay. And yeah, this is another example. Please go through yourself, right? Then one more example. Here we have to show 2 points are critical points. All right, I already tell you the 2 points are critical points. The calculation is a little bit more, so you have to solve a system of two equations to find the x, y value. Global minima and maximum, which means absolute maximum and minimum. When all the points in the domain, right, comparing to the critical point, function value at the critical point. If it's greater than the value at the point, so it's an absolute or global maximum. If it's less than, it's a global or absolute minimum. Similarly, as a single variable calculus. Steps for finding absolute maximum and minimum. So f is continuous function of two variable on the closed and bounded. Okay, whenever we talk about absolute maximum and minimum, extreme value theorem gets involved, which means we require the domain to be closed and bounded. Right? Locate all critical points, because closed and bounded sets includes two parts. First part is called open set, right? Open set. And then, so we use U in this case for open set. On the open set, we can find, because a function is differentiable on open set, we can find all critical points by setting the gradient to be 0. On the boundary point, right, find all critical points on the boundary point. So this partial U means boundary points. Then we compare all the values, evaluate at the critical points and the boundary points. Right? We compute the values of f at all critical points and at all boundary points. Then we compare them. Whoever value is the highest is the absolute maximum. Whose value is the smallest, the point is absolute minimum. So it's analogous to single variable calculus. So let's see this example. We want to find maximum minimum for this function, right? And in the disk D defined by this, we see this is a closed and bounded set, right? The open set is x squared plus y squared less than 1, which is the disk without the circle. The boundary points are x squared plus y squared equals to 1. The circle, the unit circle, is a set of boundary points. So what do? We just 4 steps. So finding all critical points, right, by finding the gradient, by setting the gradient of the function to be 0, then we find that half and a half is the critical point on the open set x squared plus y squared less than 1. And the boundary point, what do we do? Boundary points are closed set, right? We cannot differentiate a function on a closed domain. So what do? We use parameterization. So a unit circle can be represented as a C of t equals sine t cosine t, and t runs from 0 to 2 pi. So we do a composition of this function. So f composed with c, right? We change this function. F composed with c, we can rewrite the function as this. We can rewrite this function as this. So to find the maximum and minimum on the boundary, it suffices to locate the maximum and minimum value of this function, right? Right? Because this function is just been parameterized of this. So then what do? We just find the derivative of g, right? Then it's set to be 0. So what is this? This is single variable calculus, single variable function. We just use single variable calculus. Right, then we solve for the angle t. So get 2 solutions, pi over 4, 5 pi over 4. So we'll have those candidates. We'll have a half. We'll have pi over 4, 5 pi over 4. Right. We'll have this. So we'll calculate the C of pi over 4, C pi over 4. Right. And the boundary points are C of 0, C of 2 pi. Then we just compare them. So f takes C of pi over 4, we get 2 minus square root 2. F takes C of 5 pi over 4, we get 2 plus square root 2. Takes 0, C of 0, we get a 1. C of 2 pi is the same as C of 0, we get a 1. So obviously 2 plus square root 2 is the biggest value. And 2 minus square root 2 is less than 1. So it's the smallest value. So we see it's clear that absolute minimum is half. Oh, yes, we have this half. F of half equals half. And because square root 2 equals 1.41 something, so 2 minus 1.41 is a little bit bigger than half. So that's why this half is the absolute minimum. And this one is absolute maximum. No, Gregory, present next class. We present at the beginning of class. It serves as a review. Okay, anyone has any question about this? So example 11 is a little bit complicated. All right, it uses our parameterization skills. Anyone has any question about 11, example 11? All right, you have enough homework to do for this one, all right, for this section. And please do your homework. Okay, no more presenting 3.1. All right, 3.1 is being presented enough. 3.2, if you want to present 3.2, 3.3, choose some interesting questions. And make sure you really understand the question, okay? And understand your solution, because prepare, I sometimes ask you questions. And ideally, you present this one. This is a 3.3, okay? Ideally, tomorrow, you present 3.3, all right? Okay, anyone has any questions? Gregory, I understand that, but let's do tomorrow. Let me change our homework. Right, chapter 3. Let me see chapter 3, how many sections? So next class, we're going to talk about Lagrange multiplier. Very important concept, Lagrange multiplier. So 3.4, talk about Lagrange multiplier. Very important concept. Let's see, 3.5. is optional, so I won't put any questions. You may do the homework of this, but I won't put any questions from 3.5. All right, but 3.4 is super important. I think that's it. That's chapter 3. So by Wednesday, we will finish chapter 3. Right. By Wednesday, we will finish chapter 3. So by tomorrow, we will finish Lagrange multiplier. Tomorrow is 2. So midterm is too early, I guess. So if we put, is midterm too early? If I put testing in the chapter 1, 2, 3, because you only have 1 day to study. Tomorrow is for, oh right, it's my first. Tomorrow is your first. So you have right. You still only have 2 days to study. Is it good enough for you? 2 days of study. Right. So I'm worried about 2 days. So let's change our midterm a little bit. Let's see. But our final is on 17th. So if we do the midterm too late, it's not good either. Okay, so let's do on Monday, 7th. How about that? Because you have the whole weekend to study. So I'm going to postpone all the homework to 7th, and we're going to do our first exam on 7th. All right? Because you have the whole weekend to study for it. So I'm going to move our midterm here. All right? So bingo, that fixed the problem. That fixed problem. Let me go to announcement first. Change our exam date to be 7th. Then I'm going to change the due date of your homework. I will cover 3 chapters. Then your homework. So homework 1. Oh, 7th. I pushed it for too long. 07, August 07. Okay. Homework 2, 7. I push the 2 for the back. No. 7. Homework 3. Seven. Okay, then let me share my screen with you. Let me share my screen with you. Oops. So I'm going to create. So under this, by the time on August 7th, you will see midterm button here, just like the homework. All right. Homework button here. You click on it, you do it. And you need to have your camera working. All right. So I could see you. I could see it's you are taking the exam. Oh, you can't see the screen?
Yeah, Professor.
Yeah, we can't see your screen, Professor.
Oh, I can't see my screen. No? Oh, you cannot see my screen. Let me do one more time. Can you see it? I'm here. You see here it shows homework 1, homework 2, homework 3 until
Yeah.
homework 1 submission. Yes. Yeah. So on August 7th, you will see midterm button right here. You click on it, the midterm will be there. All right, you have to click on that. And then you submit your homework, your exam from there. Just same as you submit your homework. But What more is you need to turn on your camera so I could see you. All right, so I'm going to change the announcement a little bit. I'm going to add the announcement, tell you the details. So make sure you have a working camera so I could see you during the exam. So make sure you have a working camera. Right? And yeah, you will see midterm appear as same as appear the way same as your homework. Submit. So what else? Is this clear? Let me see your comments. Yeah, optional sections are optional. Remember, you only have to do 25 sections for homework. Even that only that totally 28. So that means you can leave 3 as optional. So 3.5 is optional, yes. The exam format, there's no multiple choice. All right, some questions may be easy, some questions may be difficult. You have to offer your answers, your detailed answers, all right? Will 3.5 be on the midterm? No. 3.5, any chapter optional, it won't be on the exam. 2.6 won't be on the exam. Any optional won't be on the exam. Okay. Optional sections won't be on the exam. Okay, any other questions? Oh, make sure you have your ID. Make sure you have your working camera. Make sure you have your ID. Make sure you have a picture ID. Ideally, student ID. Will it be multiple choice? Nope, no multiple choice. Yeah, you upload your work just like that, just like normally, just like your homework.
You can show
Submit.
the digital ID, right? Oh, sorry.
CUNY ID would be ideal.
Okay.
Picture ID, like your driver's license, but the CUNY student ID, ideal. If you don't have a CUNY student ID, you have a state ID, it's fine. I just need to see, I just need to match your face, match your lovely face with your picture ID, all right? To make sure you are the one who's taking exam. Yeah, you submit with your exam, but you only have to submit. You only need to write down the number, okay? If you, the solution 1, right? You put the number 1, then you offer your solution. You don't need to rewrite the questions. No need. Just write down the question number. Yeah, optional 2.6, 3.5. You're right. Optional sections. Let me see. Like 2.6 and 3.5 will be on the midterm. Any other questions? What about the ID? We have to submit also, yes. Yes, submit your solution the same way as you do your homework. Important. Put your ID alongside of your solutions. Just make sure that's yours, okay? Put your ID alongside of your solutions. Because you know everything's online, right? Just make sure you know everything's fair to everybody. No one is cheating through. No, you don't have to submit it before. You will have your picture ID with you when you take your exam. So I will check your ID with your lovely face. And then when you submit your solution, your picture ID need to be, when you take a picture of your solution, right? When you take picture of your solution, you need to put your ID alongside of your solutions. All right. Put it on the corner, put on top, put on the bottom, put on the, you know, on the other side. Doesn't matter. But you have to put your ID on the along with your solutions. Yeah, I will give you extra time for this, so not to worry about the time. So your exam time is 2 hours. All right. So I'll give you like 10 or 15 minutes to upload your work. Dayeli, what's your question?
Yeah, just a quick question, because usually our PDF allow or just what the word needs to be written on paper.
I'm sorry, I didn't get your question.
Hello?
Yes.
Yeah, can you hear me now?
Yes.
Yeah, I was just asking, our PDF allow or do our work need to be written out on paper?
No, use PDF. What do you mean? You want to answer
PDF, so
your
like electronically, because usually I do my work on my iPad. So like I write it out and then I create a PDF and then I can upload that PDF onto Blackboard. I don't know if that's allowed or not.
No, it's not allowed. You have to use a pen or pencil.
Okay, got it. Thank you.
It has to be handwriting. You have to take a picture. You may convert into, ideally you can convert into a PDF file, one PDF file. Has to be handwriting, has to have your ID alongside of your handwriting. Okay, you guys, see you tomorrow, okay? Enjoy doing your homework. Thank you.